We now look at solving trig equations using cofunctions. But before we get there, there is a concept that we need to understand, which is trigonometric equations where we equate angles. Okay, so what I have written here is various scenarios. So if we look at the first one, if I have sine A equals sine B, everything is the same except that the angles are different. And if everything is the same except the angles, it would make sense that we can equate the angles, right? Because the left-hand side is equal to the right-hand side after all, okay? But we have to remember that when solving a trig equation, our answers lie within various quadrants. So in this case, if I take my key angle as the second angle, given in the right-hand side, okay, the sign also tells me whether, the positive or negative sign tells me which quadrants to write my general solution in. So this whole right-hand side is positive, which means that for a sign being positive, my general solution will be in quadrant 1 and quadrant 2. So quadrant 1, I write my solution as the angle, which in this case is A, equal to the key angle, which is the angle on the right-hand side, which is B, plus multiples of 360 degrees. Okay, and then I have a second solution in quadrant 2. Again, it's my angle, which is A from the left-hand side, equal to, now in quadrant 2, we write our angles as 180 degrees minus the key angle, which in this case is my B, plus K times 360 degrees. Okay. Looking at the equation below that, I have sine A equals negative sine B. Okay. So I have the sine A and the sine B again, which means I'm going to equate my angles. But what this negative here tells me is which quadrants I'm going to be working in. Okay, so if it's negative and I'm dealing with a sine function, my solutions will lie in quadrants 3 and quadrants 4. Okay, so remember when we deal with trig equations, the sign always just works to tell us which quadrants our solution will lie in, and it's the same here. Okay, so I go to my third quadrant. The angle, which is A, is equal to, in this case, 180 degrees plus my key angle, which is the other angle from the right-hand side, B, plus multiples of the period, which is 360. Okay, going to the fourth quadrant, I have my angle, which is the angle on the left-hand side, equal to 360 degrees minus the key angle, which is my B, plus multiples of the period. Okay, so that's for cos. If we move to this, that's for sine. If we move to cos, it's the same principle. Okay, I have cos A equals cos B. Everything is the same except the angles, so I can equate the angles within the quadrants. Now, my right-hand side is positive, so if it's positive, I'm working in quadrants 1 and quadrants 4 for cos. Okay, so the general solution from quadrant 1 is my angle, which is the angle from the left hand side, equal to my key angle, which is the angle from the right hand side, plus multiples of the period. Okay, in quadrant 4, I have my angle equal to 360 degrees minus the key angle, plus multiples of the period. Okay, now I have if cos A equals negative cos B. Okay, again I have cos. Yes, I have a negative, but that just tells me which quadrants to work in. So if cos is negative in quadrants 2 and quadrants 3. But I have cos A, cos B. So that B is going to be my key angle again. So quadrant 2, I have my angle, which is A, equal to 180 degrees minus my key angle, which is B in this case, plus multiples of the period. Okay, going to quadrant 3, I have my angle, which is 180 equal to 180 degrees plus the key angle, plus k times 360. Moving to tan, okay, it's the same type of principle, except for the tan graphs, we don't have to write a general solution in both quadrants, okay, because of the period of the tan graph. So if tan A equals tan B, okay, my left-hand side is positive. Tan is positive in quadrants 1 and quadrants 3, but because the period of the tan graph is 180 degrees, and it takes me 180 degrees to get from quadrant 1 to quadrant 3, I don't have to write the second quadrant's general solution. Okay, it's covered in the first quadrant. So, again, everything is the same except the angles. So I'm going to make my angle A equal to, and use the second angle B as my key angle. So that's equal to B, plus K times the period. Okay. Then I have if tan A equals negative tan B, again, that negative just tells me which quadrants I'm working in, quadrants 2 and quadrants 4, but because of the period of the tan graph, I don't have to consider the second quadrant there, the second of those two quadrants. Okay, so again, quadrant 2, again, my angle A is equal to, in quadrant 2, we name our angles 180 degrees minus the key angle, which is B, plus K times the period of the tan graph. Okay, now I just want to look at one example that is numerical, applying what we've just learned. Okay, so I have sine theta equals sine 60 degrees. Everything is the same except the angles. So I'm going to make the angle on the right hand side my key angle. Okay, and to know the quadrants, I look at the sign of the right hand side and it is positive. So my general solutions will lie in quadrants 1 and quadrants 2 for the sine function. Okay, so quadrant 1, my angle, which is theta, is equal to the key angle, which is 60 degrees, plus K times the period of the sine graph. Okay, then in quadrant 2, my angle, which is theta, is equal to 180 degrees minus the key angle, 60, plus multiples of the period. Okay, and I can simplify this. 180 minus 60 is 120 degrees. So there are my two general solutions to this equation. Okay, now we take that knowledge into what we are going to do here, which is using cofunctions to solve equations. Okay, so here we are told to solve for theta if sine theta equals cos 60 degrees. Okay, so I have sine and I have cos, and the angles are different. Now, previously, if we had sine and cos in our equation, we either tried to bring everything to one side and factorized, or if we couldn't do that, we brought them on either side of the equal sign and divided by cos to change it to the tan theta. Okay, but our angles are different, so we cannot do that. Okay, then if we had a squared term, we tried to replace it with something from the square identity, but none of that is applicable here. So we need a fourth method of solving this, and that is using the fact that sine and cosine are co-functions. Okay, so just remember that if we have an angle sine x, that is equal to cosine of the complement of that angle. Remember, angles that add up to 90 degrees are complementary angles. So if I have sine 30 degrees, that is equal to cos 90 minus 30, which is 60 degrees. The 30 and the 60 add up to 90. They are complementary angles, and we go to the cofunction. Okay, we are going to use that background for this. Okay, so sine theta equals cos 60 degrees. To solve this equation, what we want is a situation that we have been looking at in this video, where we have sine of an angle equal to sine of an angle, so that we can just equate the angles. Okay, so we want to change this cos to a sine. Okay, so I have sine theta on the left hand side. Now I want to convert or reduce this to its co-function. Okay, so yes, you might already see what it should be, but I'm just going to show you that cos, if I keep the value of the angle the same, okay, so I keep cos because I'm writing 60 as 90 degrees minus 30. The value is the same. If the value is the same, I have not yet changed the function, okay? But as soon as I reduce to the complement, then I go to the co-function. So sine theta equals, going to the complementary angle, I change it to sine 30 degrees. Okay, so cos 60 is equal to sine of the complementary angle. Okay, but now what I have is the situation we've been looking at. Sine theta equals sine 30 degrees. The only thing that's different is the angles. So I'm going to use the 30 degrees as my key angle, and the right hand side is positive. So my general solutions will lie in quadrants 1 and quadrants 2 for the sine function. So quadrant 1, my angle is theta, which is equal to the key angle 30 degrees plus k times the period of the sine graph. Okay, and then in quadrants 2, my angle is always 180 degrees minus the key angle, which is 30, plus multiples of the period of the sine graph. Okay, and that simplifies to 150 degrees plus k times 360. Okay, right, just a quick note. If you are wondering whether you could have changed these both to cos, yes, you absolutely could have. Okay, it works both ways. Okay, final example, which is taking everything we've learned so far and just looking at a slightly more complex equation. Okay, now what we have is sine 2x plus 30 degrees equals negative cos x minus 15 degrees. Okay, so notice that we have sine and cos. The angles are different. Because the angles are different, I can't factorize. I cannot use the quotient identity to solve this. So I have to use co-function reduction. Okay, so what I'm going to do is change my right hand side to the co-function. Yes, you could change the left hand side. I'm just sticking to a set method of always changing to the right hand side, but it does work both ways. Okay, so what I'm going to do is I'm just going to block this out for now. Okay, so I don't want you to get confused. So just don't let that complex angle muddle your brain. Okay, just block it out for now, literally. Okay, now we want to reduce this to its co-function. Okay, so I keep the negative there. Now the co-function of cos will be sine of the complementary angle. Okay, now if this was negative cos A, okay, it would reduce to negative sine. What is the complement of A? It is 90 degrees minus A. But now my angle is not A, it is x minus 15 degrees. So in my bracket here, I will have 90 degrees minus x minus 15 degrees. Okay, pause here if you need to just compare these two and convince yourself that this is correct. Okay, so what I have on the left hand side is still sine 2x plus 30 degrees, okay? But if I look carefully, I have sine and sine, okay? The angles are different, but I can now equate them, okay? Now remember that the positive or negative tells me which quadrants I'm going to work in. So because it's negative, sine is negative in quadrants 3 and quadrants 4. So that is where my general solutions are going to lie, okay? So in quadrant 3, okay, the way I write out the general solution is the angle equal to 180 degrees plus the key angle plus k times the period, okay? And in quadrant 4, I write it as the angle equals 360 degrees minus my key angle plus k times the period of the graph. Okay, so just remember that because we are working with complex angles here. So my angle I take from the left hand side is 2x plus 30 degrees equals 180 degrees plus my key angle is the angle from the right hand side here, okay, which is 90 degrees minus x minus 15 degrees, okay? Then I add multiples of the period of a sine graph, which is 360. Okay, I've got my equation, now I simplify. So get rid of the brackets. I have 2x plus 30 degrees equals 180 degrees plus 90 minus x plus 15 degrees plus k times 360. Okay, now I can add and subtract like terms. So I have 2x and I'm going to add another x. So I'm going to be left with 3x equals, then I have 180 degrees plus 90 plus 15, and that gives me 255, and I'm going to subtract 30 degrees, so it gives me 225 degrees plus the k times 360 that I still have. Okay, I still need to solve for x, so I'm going to divide by 3. I divide every term by 3, so I'm left with x equals 225 divided by 3 is 85 plus 360 divided by 3 is 120 degrees. So that is the general solution from my third quadrant. Okay, looking at the fourth quadrant, my angle is 2x plus 30 degrees equals 360 degrees minus the key angle, which is from the right hand side 90 degrees minus x minus 15 degrees, and then I add k times the period. Okay, so simplifying this, 2x plus 30 degrees equals 360 degrees minus 90 degrees minus minus, so that's plus x, minus minus minus, so that's negative 15 degrees plus k times 360. Okay, so adding like terms, 2x minus x leaves me with x equals, and then I have 360 minus 90 minus 15, and I'm still going to subtract 30, gives me 225 degrees plus k times the period. And that is my second and final general solution for this.